According to McKinsey's State of AI 2025, 88% of organizations now use AI in at least one business function. But in any given function, no more than 10% are actually scaling those agents. Most builders assume this massive drop-off happens because the underlying models aren't smart enough yet. The data proves otherwise. The most cited reason teams pull their agents back from production is operational visibility. Once the agent is deployed, the engineering team loses the ability to see how it makes decisions. The teams that ship and keep their agents in production are the ones who can answer the question, why did the agent say that, in under 5 minutes? If you cannot trace that decision path, the agent becomes an unreadable black box. That is when the forced rollback happens. Fixing this requires a specific architecture. We need to look at the structural differences in agent traces, map the specialized observability platforms, adopt standardized telemetry, and enforce rigid operational metrics. Achieving that 10% production threshold is impossible until you make the AI's internal logic perfectly legible to your engineering team. This diagram maps a traditional microservice trace. A request comes in, hits a service, routes to a database, checks a cache, and sends a response. The code is deterministic. Errors throw explicit exceptions, and latency is measured by the wall clock. Agent traces do not look like this. 40 years of distributed systems wisdom only partially applies to an architecture built on multimodal, nonlinear components. The first major difference is stochasticity. You can feed identical inputs to the exact same agent on the same day and get completely different outputs. The trace must capture the actual decisions made at every single model call, the exact prompt, the model parameters, and the raw response. The second difference is how we log tools. A traditional trace logs an external API ping. An agent trace has to log that the agent decided to execute a password reset search, specifically because the user asked about it. The reasoning itself is part of the data. Vector search involves a specific series of metadata: query embedding hashes, top K remits, and the actual chunk IDs returned with their exact re-rank scores. If a customer asks why the agent quoted a specific article, the trace must provide the content and score that drove that decision. If you apply legacy tracing to an LLM workflow, your monitor will show a fast, error-free HTTP 200 success code, even if the agent is actively outputting completely fabricated information. This grid lays out the 6 major architectural platforms in the current observability market. None of these tools are interchangeable. Each optimizes for a specific part of the job. Langsmith provides the native requirement for LangGraph architectures, offering deep visualization for graph-based agents. If you want observability inside your own VPC, LangFuse is the open-source default. Arise Phoenix offers the deepest evaluation primitives for drift detection. For teams needing a lightweight build, Helicone acts as the simplest drop-in proxy. Change one base URL and you get traces. Then there is Datadog LLM Observability. This is the enterprise default for shops already heavily invested in standard infrastructure monitoring. But a monitoring-first approach assumes system visibility equals behavioral visibility. An LLM can return a fast, error-free response that is entirely wrong, and infrastructure monitoring cannot see the error. Finally, Weights and Biases Weave serves teams that require strict continuity between their model training environments and production execution. Selecting an observability platform based on legacy infrastructure habits blinds the engineering team to confabulation. You must pick the tool that matches your specific AI architecture. The industry has converged on a universal telemetry schema that functions across all of these major backend vendors, the OpenTelemetry GenAI semantic conventions. This diagram shows the universal core attributes feeding into a central pipeline. We track the exact vendor system, the precise model version, and separate counts for input and output tokens to accurately analyze cost. We also strictly define operation naming attributes. Every single action is definitively categorized as an agent invocation, a tool execution, or a retrieval operation. On top of that standard schema, we layer custom workload attributes. This tracks business-specific logic like customer IDs, tenant boundaries, or escalation triggers. Failing to adopt this strict standardized schema from deployment day one guarantees a massive technical and financial penalty when you migrate vendors in the future. Isolating true customer utility requires filtering out system noise. For a help desk stack, we focus on 8 specific indicators that cover the vast majority of on-call investigations. This dashboard highlights the first threshold, latency. We set the P95 response limit at 5 seconds because user abandonment spikes immediately once the agent takes longer than 10 seconds to answer. Next, we track token costs. These must be recorded as entirely separate line items for LLM generation, vector embeddings, and re-rankers. Grouping them masks ballooning expenses. Metric 3 is the retrieval hit rate. We require a fraction of search calls to return at least one chunk with a re-rank score above 0.5. Drift in this number signals that your knowledge base is degrading. For safety, grounding judge block rates must stay under 5%. Spikes in the guardrail block rate clearly indicate an adversarial attack or a misconfigured policy. A healthy escalation rate for Tier 1 support sits between 25 and 35%. That feeds into the headline metric, the overall resolution rate. An on-call engineer gets an alert at 2 a.m. By following a structured 7-step diagnostic loop, we can reduce the time to resolution for silent failures from hours to about 15 minutes. Step 1 is isolating the specific conversation ID. From there, the trace UI maps the exact sequence of tools the agent independently decided to execute and the order it called them in. Step 3 requires opening the vector retrieval subspan. The engineer audits whether the correct knowledge chunks were actually surfaced to the model and if the scores were high enough to trust. Next is the diagnostic fork. The engineer compares the retrieved data chunks directly against the final response. This isolates whether the failure was a bad search or if the LLM hallucinated the answer. Then, they run the final safety audits. They check the grounding judge and the guardrail hooks to determine exactly why the automated safety net failed to intercept the bad response. Closing this loop by writing a deterministic evaluation case prevents recurrence. It is the exact operational mechanism that transforms an unpredictable AI into a hardened, scalable asset. Attempting to monitor an AI agent using microservice logic guarantees failure. It completely ignores the stochastic nature of the model and hides what the agent actually decided. The OpenTelemetry GenAI conventions are the non-negotiable cross-vendor foundation required for any serious production build. True operational maturity is defined exclusively by adhering to the 8 strict metrics and mastering the 15-minute diagnostic loop. That operational discipline is the dividing line. It separates the mass of organizations trapped in prototyping from the elite 10% that successfully scale AI. Tomorrow is the finale, rolling out to production. Advanced deployment strategies like shadow mode and canary releases rely entirely on the telemetry architecture we established today. Instrumentation provides the discipline required to answer, "Why did the agent say that?" in minutes instead of hours. That single capability determines whether an agent survives in production.